Excellent. So first things first, just in case people haven't got their block course notification email yet. Come on. Cool. Take a note. This is where, so obviously you'll all be doing your block course in Wellington, but Thomas, Ollie, Michael and Ian, you guys will be joining us on the 28th of the 4th for 2 weeks. And then Spencer, Thomas with an H, Sebastian, Liam and Leighton, you guys will be joining us from the 12th of the 5th for 2 weeks. So those are your block course dates. Take a note of that. It'll also be on the video for you guys to look at later. Cool. So we have finished all the night classes on transformers. And so now we're going to start looking at motors and various things to do with motors. So first thing we're going to look at is we're going to look at a little bit of motor terminology. Everyone see that? It just wasn't showing up on my other computer screen. Sweet, cool. So yeah, motor terminology. So first thing we need to look at is horsepower. So horsepower is a little bit antiquated as far as we are concerned here in New Zealand, just because we don't really use horsepower. Everything apart from with cars. All good, Seb. So yeah, we don't use anything for with horsepower apart from cars. But even then, we still measure a lot of our power for cars in kilowatts, especially if you go take your car to the dyno. So because of this, we do have a lot of old motors that are rated in horsepower. And so horsepower, you can see from the image there, is basically how much force it requires to lift a weight of 550 pounds, 1 foot in 1 second. That is the definition of horsepower. Using a lever like this, how much power does it take to lift 550 pounds, 1 foot off the ground in 1 second? That's how we get a horsepower. Cool, but all we really need to know is that 1 horsepower is equivalent to 746 watts. It's really 745.7, but for ease of math, we use 746. So if you're ever given a question in an exam, so how much you've gone to a job, you have found that the motor's faulty, it needs to be replaced, it's a 3 horsepower motor. So you need to replace it with the equivalent in kilowatts. So we take 3 times it by 746, and we get 2,238 watts. Or you would use a 2.3 kilowatt motor, because that's probably as close as you can get in terms of kilowatt ratings at that size of motor. Cool. So the next thing we look at, torque. So that's another thing that's very important with motors and cars. So torque. So what is it? It's one of the many words around motor characteristics. Motors provide torque in order to complete a task. But what is torque? So people say torque is a force that acts in a circle. So it's a rotational force or a force that works around a point. Well, this is on the right track. Torque itself cannot be defined as a force. Force is an influence to change the motion of an object in any way, shape, or form. Force can be linear, such as pushing an object in a straight line. We've learned about other types of force, such as EMF, electromotive force. It's a force that causes electrons to move, resulting in current flow, and we get magnetic flux. So torque is a measure of force that causes something to move around in an axis. This means that instead of applying a linear force to an object, it's a twisting force applied instead. It can also be looked at as acquiring angular acceleration, as the force applied to it at an angle of the object being moved. Cool. So torque is measured in Newton meters, force measured in newtons, and radius is the radial distance. So your torque is equal times as your force times your radius. So let's have a look at that. where is pen? Cool. So we would have a look at that. So we're using this formula. So want to find out the torque of a motor. So it's applying a force of, say, 3,000 watts or 3,000 newtons, sorry, at a radius of, measured in meters. So let's go half a meter. So that results in a torque of 1,500 Newton meters. Make sense? So if we do the same thing again, but we take that same force of 3,000 and we use a radius this time of 1.5 meters. This time instead we're going to have a torque of 4,500 Newton meters. Sorry, that should be small m. Cool. So we use the same force but increase the size of the lever, which is basically what this cog is. It's a lever. We increase the torque. But obviously, as we increase the torque, we reduce speed because we've made that lever bigger. It's now spinning at a slower speed. So slow speed but high torque. And that'll come in be important later. Cool. So then we talk about load torque. So from the formula we looked at, we can see the torque is proportional to both the force applied and the radial distance from the turning point. Easy way to visualize how torque works is opening a door. A door requires a certain amount of torque to overcome the friction in the hinges and just the weight of the door. So the torque requirement is called load torque. So we have no doubt noticed that sometime in our lives that it's harder to open a door the closer to the hinges you push on it. Conversely, it's easier the further out from the hinges you push. This is because you are extending the radial distance from the turning point. The further you are from the turning point, the easier it is to overcome the load torque. Yeah, you can see on the bottom right there, turning moment. Same work needs to be done. Half the distance requires twice the force, and half the force at twice the distance. It's the same if any of you guys have tried to change a tire and the nuts are really stuck. Basically, you extend the lever of the handle and your force gets multiplied. So that lever is considered a force multiplier because you're using the same amount of force, but you've increased the torque. Cool. So now we can look at torque, energy, and power. So we've looked at applying force to an external point to create torque in the center of a radius. A motor does the opposite. It creates torque in order to overcome the load torque that is positioned away from the center line on a radial line. Thus, the greater the distance from the turning point, the greater the torque must be to move it. So we have a formula here, P equals 2 pi nt over 60. So this is P is the output power of the motor measured in watts. N is the rotational speed of the motor measured in revolutions per minute or RPM. And then T is the torque of the motor measured in Newton meters. The 60 converts the revolutions per meter into seconds because when we do this calculation, we need it in seconds, not minutes. Cool. So torque production. So torque in an electric motor is produced by two magnetic fields interacting with each other. So you've got the windings of the motor, bunches of the same conductor coiled together. The way in which they are coiled produces an electromagnet and is concentrated in the metallic core of the motor. The concentration of this magnetic flux creates a magnetic pole, north or south, depending on which direction the current is flowing. A magnetic field is also set up within the rotor of the motor. This can be done a couple different ways. The rotor is connected to an external circuit via a commutator or slip rings, the rotor has an EMF induced into it via electromagnetic induction. So Fleming's left-hand rule. So you guys remember or have you guys been taught the Sparky gang signs? The left and right hand? Okay, good. I'll assume you all remember them then, but we'll go over them just in case. So it's right and left, so you generate. So the right is for generators, and left, you use what's left. So the left is for the motors. So if we know the direction of the current flow and external magnetic flux, we can determine the direction of the conductor will be forced to move in. Using the diagram here, we can better understand this concept. It shows the external magnetic flux directed towards upwards to the South Pole. The current flow in the conductors is moving towards us and the conductor, the top of the diagram, and away from us in the bottom conductor. The flux around the conductor bends with the external flux. However, the external flux would prefer to be as straight as possible, so we'll force the conductor out to the left. This is the point at which torque is produced. All electric motors produce a rotating magnetic field around the outside in one way or another, so this process of pushing the conductor inside the rotor to one side is continuous, ensuring that the rotor is constantly moving around in a circle, either being pushed by or chasing the magnetic field. Cool. So let's look at some torque terms. So we've talked about load torque. It's the torque required to shift the weight of the load. It's a characteristic of the load to do with the motor. Starting torque. This is the maximum torque a motor can produce upon startup. There's often a different value to full load torque, or FLT, depending on the motor, but must always be greater than the load torque. So the starting torque must always be greater than the load torque. Your driving torque, so the amount of torque the motor will produce as it accelerates from startup towards full speed. And pull-out torque, the maximum torque a motor can produce if the load torque exceeds the pull-out torque, the motor will stall. So load torque exceeds the pull-out torque, the motor will stall. The maximum torque a motor can produce, so that's the maximum rating. Above that, you're overloading it, and then the motor will more than likely stall. Cool. So your running torque. So this is the point where the driving torque will equal the load torque required to shift the load. It is the balance of which a motor should be designed to operate at a given speed. So your running torque at normal speed may vary depending on the load, but if selected correctly, the motor should run at a reasonable range of these values. This can also be called the full load torque. And then stall, so being stalled is a state that a motor can be in when it cannot develop enough torque to overcome the load. The motor will continue to try and will draw excess current as it does until either it burns out or trips the circuit protector device. Because this diagram represents a motor running under normal operating conditions. So at startup, the motor begins at a lower level of torque, but increases as speed increases. At a certain speed, the motor will stop producing any more torque, and the level of torque produced will reduce until it meets the requirement of the load torque, where it will sit happily at that speed. So you see the starting torque is lower, and so the driving torque is as it's pushing up towards speed. It meets the pull-out torque, and then it drops down to the running torque. So this is the point where the load is moving and the motor is spinning, and it's sitting comfortably at the desired speed, and it doesn't need to then keep driving up. So how many of you guys are into your cars and stuff? And you guys seen them take cars onto the dyno? Okay, well, if you go and watch any videos like I hate to push them, but Mighty Car Mods, they do a lot of they modify cars and then take them to the dyno to see what kind of kilowatt graph or torque graph. So basically you'll watch the motor, it'll be speeding up, hit the driving torque. It'll hit the pull-out torque where the RPMs kind of start to hit the limit and it can't go any higher. And then when they take their foot off the accelerator, the torque drops down. And then, so you would see the same graph if you were accelerating. So starting torque, the driving torque, the pull-out torque, and then it drops down and it hits the running torque. So it matches the speed that you're driving. So sometimes you'll notice if you're accelerating up to speed, you see the RPMs go up, and then as you meet your speed, you ease off the accelerator a little bit, and the RPMs drop down, and then they ease out and just sit there at the running torque. Cool. So this diagram represents a motor that is not rated for the load. So go back. So you see the load torque there, that line at the bottom. So its starting torque's high to the driving torque, reaches its pull-out torque, that's the pull-out torque, and then it's got the running torque down there where it's met the load torque and it's sitting there at speed. So this diagram, you see the load torque there is too high, so the starting torque isn't high enough to meet overcome the load torque, so it will just sit there stalled. And it's a very nice sound. We replicate it here in the training center a couple of times, and it just sits there whining. It's a very not nice sound, and we turn the motor off really quickly. So it represents a motor. It's not rated for the load. We can see the load torque is much higher, exceeds the starting torque produced by the motor. Because the motor cannot get the load moving, it will stall upon startup. It's dangerous as the motor will continue to draw current to try and magnetize the rotor. If the motor were to be run up to a speed and then the load connected, it would run. However, there is very little room for excess load, which will result in the overloading at speed, causing the motor to stall. So what happens is the motor sits there, it draws current, puts current through the windings, but because the fan isn't moving, it's not pulling any air through the motor. So those coils are just sitting there, heat soaking, and then as it heats up, the resistance increases in the copper winding. So that draws more current, and then it just eventually will burn out. Cool. So when we talk about motor efficiency, so the calculations we've done with the torque and speed have all resulted in a power rating of a motor. So the power rating is the same rating that you would expect to see on the nameplate of a motor, as is what the the motor is capable of supplying. This is called the output power of the motor. So due to certain factors within the motor, the amount of electrical energy supplied to the motor is never the same amount of rotational kinetic energy delivered at the shaft of the motor. Energy is lost in the middle somewhere, which is what we're going to look at in this chapter. So, so whenever you buy a motor, you buy it at a rated output, not input. So if you look at the motor, it will have output power, but it'll also have a power factor and efficiency. So basically the power factor and the efficiency you need to take into account, and then we'll learn calculations later. And then we can think in third year you do it, maybe at second year block course as well. You talk about the efficiency, the power factor, and that will then determine the current draw, which you need to allow for. And also we need to be aware, because that a driving torque like that, it pushes a lot of current through the motor really quickly. We need to design circuit protection for the motors in a way that they will handle that inrush current. So most of the time you'll use motor-rated fuses or a motor-rated circuit breaker, which can allow that inrush current for a short period until it reaches its pull-out torque or reaches the load torque. Cool. So losses. So there are 4 types of losses in a motor. So you've got your windage, your heat, your copper losses, and your iron losses. So just like a transformer, because there's a magnetic field involved, we do have iron losses, and we have copper losses because, like a transformer, we have windings. So windage is the energy lost due to friction of the rotor turning against the air around it within the frame of the motor. So there's not a great deal of resistance opposing a cylinder as it rotates, but it still does exist. Windage is also comprised of friction against the air created by the inbuilt fan that most motors typically have mounted to the rotor shaft. So this fan is used to circulate air around the motor to keep it cool. As the blades press against the air, friction is created, which results in loss in power ability. Some motors don't have a fan on the back. Some common ones are water pumps, especially the cold water pumps. Because they have cold water circulating inside them, they do have a slight heating effect from the water. And you can get water-cooled motors for places where they don't allow airflow. So a clean room, for example, where they don't want any air movement because of dust, such as pumps that share the same room as a computer room. Very rare, but yeah, anything where there's not allowed to be airflow, you do get water and sometimes oil-cooled motors, but these are very rare, and I've never seen one in person. Cool. Then you've got your heat losses. So heat is wasted energy created by the mechanical friction of surfaces rubbing together. This includes the bearings that support the rotor shaft in the center of the motor. A good set of bearings have reduced friction and thus losses. However, over time, bearings start to wear out, leading to higher losses in older motors. It's always wise to maintain motor parts, including bearings, so that losses are kept to a minimum. So if you've got motors in a factory, you may have a maintenance schedule shut down every once in a while, at which point the machinists will go around and kind of disconnect the motors from the cogs, belts, whatever, machines, and they'll just spin the motor freely with the shaft and listen and feel. And yep, that bearing's good, or nah, bearing's gone, pull it out, chuck a new one in. A $50 bearing is much cheaper than a $5,000 motor. Cool. So then you've got your copper losses. So all conductors have resistance because they're copper. Ideally, the lower the better, but it's never possible to eliminate it entirely. As current flows through this resistance, which includes the stator and sometimes rotor windings, we'll look at what is the stator and rotor in a little bit. Energy is converted into heat. So these losses can also be called I squared R losses because it's current and resistance, which can be calculated by looking at the current flow through the winding and the resistance of the winding. This also applies to transformers and must be included in calculations to ensure that the equipment is supplied appropriately. Cool. And then you've got iron losses. So iron losses, so like we talked about the transformer, it's lost due to the creation of the magnetic field within the motor itself. So even though the copper windings generate the magnetic field, there are still iron parts which maintain or take advantage of that magnetic field. So a certain amount of energy is always used to magnetize the iron core and poles of a motor. Current flows within the iron core is called eddy currents, which we looked at during transformers, which do not contribute to the performance of the motor, so it's considered a loss. So hysteresis is also a type of iron loss. Hysteresis is energy lost due to the realignment of molecules within the iron core as the magnetic flux changes polarity at the supply frequency. Each time the polarity changes, molecules shift and rub against each other, generating heat and vibration. This also applies to transformers as they consist of iron cores, and the hum you can hear when near a large power transformer is the hysteresis causing the iron to vibrate and make sound. All of these losses contribute to the overall power loss of a motor and can be labelled the inefficiency of the motor, and we'll look at the overall power loss affects the motor. So yeah, again, with the eddy currents, that's why they still, even in motors, they will use laminated silicon steel rather than solid iron to reduce these eddy current and hysteresis losses. Cool. So your input power. So the power required for the motor to do its job is called the output power. Then the power required to do it plus the losses within the motor is called the input power. So this is the electrical power that will be drawn from the supply. It must be looked at not in such a way where the motor has a lot of losses, because of the amount of power being supplied, but more in a sense that the greater the losses are in combination with the power output requirements, the larger the input power will be. So the difference between the output power of a motor and the input power it requires is called the efficiency of the motor. So basically, power out versus power in. And we as electricians must design and install our circuits and fittings with the input power in mind rather than the output power. So just because it says it's a 3 kilowatt motor doesn't mean you just take 3,000 and divide it by 230 or 400 and use that as your current. You've got to take into account the losses as well for the efficiency. So now some of you may be asking, why don't we just rate the motor based on what it will consume? Because a motor is selected based on its ability to do a task rather than how much energy it will consume. The motor is designed to constantly output a set value of power, where power coming into the motor can vary due to changing values of efficiency. So this is the calculation we use, N. So N is the efficiency expressed as a percentage, and then we take the output power divided by the input power, and that times it by 100, and that's how we get our efficiency. One moment. Cool. So let's do a few examples. Man, this board is dirty. Cool. So you have cool. You have a 3 kilowatt cool. So we have a 3 kilowatt 3-phase motor, and it has an input power of 8 amps. Calculate the efficiency. Yeah, you will have to convert the amps. So assume it's running on 400 volts. Cool. And then we have a 1 kilowatt single phase motor. It's got an input current .5 amps. Cool. So what do we get for the first one? $94. Yep. Cool. What did everyone else get? Did you get the same? Yep, I'm gonna show the working. Cool, so the first thing we do is we take, so we know we've got 8 amps, so we need to find that power. So we take our 8 amps and we multiply it by 400. So our current times our voltage, which gives us 3200 watts. And then because we know N equals power out divided by power in times 100, we go 3000 because it's 3 kilowatts divided by 3200, and then we times that by 100, which ends up giving us 0.9375. We multiply that by 100, and then we get 93.75%. Cool, so we'll do the bottom one. I'll wait for you guys to have a crack at it first. Just remember, guys, when you're looking at single phase, always assume it's 230 volts unless they say otherwise. Yeah, I see where you got your answer from, Ollie. Yeah, so always assume single phase voltage, 230 volts, but they will usually give you a voltage in the question. Yeah, once you change it to 230 volts, you get 79.05. I'm still going to put the working up. So first thing we do, take our input current of 5.5, multiply that by our 230 to get our power. So 230 times 5.5 gives us 1265. Then after that, we can work out our efficiency. So we take our 1000 watts or 1 kilowatt, we divide that by 1265, we multiply that by 100, and that gives us our efficiency of 79.05%. Yeah, it's a pretty straightforward formula once you start using it. Once you guys get a bit of practice with it, it's pretty easy. So just if you're going to challenge yourself to do some practice questions with this, take your input power, divide it by your normal voltage, and then just increase the current a little bit, and then try and figure out the efficiency of that's the current. I just rounded the current to the next nearest whole or half number, just to give you guys a bit of a challenge. So that's a pretty decently efficient motor for those two. Yeah, generally you won't get anything below 70% efficiency unless it's old. Cool, and then we start looking at synchronous speed. So synchronous speed is based on the number of poles. So the stator windings of an alternator always come in pairs, or a motor, a north and a south, with magnetic flux lines in between. These poles alternate depending on which direction the current is flowing at that point in time. This means that during one half cycle, one pole will be north and the other south. And during the second half cycle, the poles will reverse. So a simple way to look at the motor is look at how the motor rotates is that during one AC cycle, a particular point on the rotor will chase the north pole and the opposite side of the rotor will chase the south. As the magnetic flux of the stator induces current into the rotor produces its own magnetic flux with its own poles. This rotor flux will seek balance and the constantly rotating stator flux. The north of the rotor will seek the south of the stator and vice versa. So let's have a look at different pole numbers. So for a two pole, a rotor that has two poles will complete a full 360 rotation within the time it takes to complete one full cycle of the supply. This is because the south pole of the rotor will seek the north pole of the motor as it starts on one side of the motor, then shifts 180 degrees to the opposite side and back again. A four-pole motor, so a motor that has four poles, will only complete 180 degree of rotation within the same time it takes to complete a full cycle of the supply. This is because the stator is wired in such a way so that when a particular pole is north, the poles 90 degrees of it and are south and vice versa. Then as the rotor flux interacts with the stator flux, the movement from north to south and back again occurs halfway around the motor. This half rotation still occurs in the same time as it would take a two-pole motor, a full rotation. Effectively, a four-pole motor rotates at half the speed of a two-pole motor. Then you got multiple pole motors. So the more pairs of poles that are added, the slower the motor will travel in relation to a two-pole motor. The relationship can be looked at as how many times more pairs of poles does that motor have compared to the two-pole. So for example, 6-pole motor has 3 times as many poles, so will travel 3 times slower, or a third of the speed. 16-pole motor has 8 times as many poles, therefore will travel 8 times slower, or 1/8 of the speed. Cool. So frequency. So the supply frequency being applied to a motor is the other factor that affects its speed. The speed of a motor is directly proportional to the supply frequency. This makes sense as the faster the stator poles change their magnetic polarity, the faster the rotor must travel to keep up with it. These two factors and the formula they are included in have been looked at before when calculating the supply frequency of an alternator, particular speed. So it looks like this: F equals NP over 60. So F is the frequency measured in hertz. N is the rotational speed measured in revolutions per minute, RPM. P equals the number of pairs of poles, always in pairs because they cannot be an odd amount of poles in a motor. The 60 converts the minutes and the speed into seconds for the base unit of frequency. Cool. The other thing we can do with this is we can use it to, we'll look at that next. So, for example, we figure out the frequency of the supply using the characteristics of the motor. So if we have a speed and we have the number of poles, we can figure it out. Cool. So let's say we have a 2-pole motor spinning at 200 RPM. Cool. Work that one out. Then we have a 4-pole motor rotating at 600 RPM. And then we have a 18-pole motor rotating at 900 RPM. So remember, it's pairs of poles. So what's the first one? Yeah, so for the first one, yeah, so basically it's a 2-pole motor, which means there's one pair of poles. So we don't need to multiply it. We basically just take our take our 200 and divide it by 60, which gives us 3.33 hertz. Yeah, 3.33. Always put the hertz. Okay, so what about the next one? Yeah. So for this one, so we have 4 poles. So we have 2 pairs of poles. So we need to take 2 poles, multiply it by 600 RPM, and divide that by 60. So we have 2 times 600 will give us 1200, and then divided by 60 gives us 20 hertz. Yeah. Yeah. 20 hertz. Cool. So now the last one. Nine? 90? Yeah, it's 135 hertz. What you do is you take your 18 divided by a half. So we know 9. 18 halved is 9. So we can multiply that by 900. and then we divide that by 60, which gives us 135 hertz. Cool, all pretty straightforward. Cool, then we go on to the next calculation we can do, which is our synchronous speed. So the synchronous speed of the motor is the speed in which the magnetic flux is revolving around the outside of the motor. It can also be referred to as the stator speed. So the synchronous speed is an important figure in our studies of motors. Some motors have rotors and shafts that are able to rotate at the same speed as the magnetic flux around the stator. These motors are called synchronous motors. They are often comprised of permanent magnet motors or doubly excited motors. So they have an exciter circuit for the rotor as well as the stator on the outside, where both the stator and rotors are connected to an external current source. So the formula for this is N sync, so speed synchronous, 60 F divided by P. So that's 60 times the frequency divided by the number of poles, because we measure speed in revolutions per minute, or RPM. So an induction motor, however, is not a synchronous motor. The rotor within the frame does not travel at the same speed as the stator flux. We'll look at that next. Cool. So give three examples. So we have a 6-pole motor supplied with standard 50 hertz. Then we have a 12-pole motor supplied at 35 hertz. Then we have a 24-pole motor supplied at 120 hertz. And yes, this is possible with variable frequency drives. So we got the first one. Anyone else? Yeah, so write the formula down here. So N synchronous equals 60 F over P. Cool. So if we use that formula for the first one, that would be, pardon me. So the first one would be 60 times 50 over pairs of poles, so 3, which would give us 1000 RPM. M. Cool. So write that over this side. 1,000. Cool. Cool. So what about the next one? Yep, 350. Yep, that's what I got. So yeah, so we take our 60, multiply it by 35, and we take that over 6, because that's how many pairs of poles we have. That will give us 350 RPM. We add that. So you guys will be given a digital capstone, but just remember, if you ever have to do a written paper or written test or written exam, you need to remember that you have to write out every step. So you would first write your formula. N sync equals 60F divided by P or PP. So therefore that equals 60 times 12 divided, 60 times 35 divided by 6, which equals this much RPM. You'll be given so that kind of question's worth 4 marks. So you're given half a mark for the correct formula, half a mark for entering the correct values, and then a mark for getting the correct answer. That's how they used to grade papers when I was doing capstone on paper. Yeah. Did my capstone on paper, but I did my theory exam on the computer. So what about the last one? Yeah, so we do take, again, 60, multiply that by a frequency, in this case, 120, and then we divide that by 12, which gives us 600 RPM. 600 RPM. Cool. Moving on. Cool. So then we have our rotor speed. So previously we were looking at, so we're just looking at synchronous speed, the speed at which the rotor travels in an induction motor is never equal to this value, and it is called the rotor speed. So the way that torque is produced by an induction motor is the relative motion between the stator and the rotor flux. A simple way to look at it is this. So like a greyhound chasing the air here, the rotor flux must constantly chase the stator flux to be moving, because if it ever caught up, there would be no reason to move anymore. The more technical description says that there must be relative motion between the magnetic flux and the conductor in order for induction of EMF to occur. Happens easily at the moment of startup as the stator flux rapidly cuts the rotor. During the startup phase, maximum current is induced in the rotor and the resultant rotor flux is established. Rotor flux then moves in the same direction as the stator flux, but can never be synchronous, because if it ever was, there would no longer be any relative motion between the stator flux and the rotor. This then would result in no EMF induction, no rotor current, and no rotor flux. With no rotor flux, there is no torque production, and the motor cannot overcome any load that is placed on it. Also, if it reaches that synchronous speed and it catches up, the current will stop flowing, so it'll actually fall behind and then catch up, fall behind, catch up, and you would lose power because of the constant build-up and crashing of the magnetic flux inside the rotor. It would be worse than just normal operation. So the rotor accelerates at startup due to the maximum current flow, but as it approaches the stator flux speed, the acceleration stops and a constant speed is achieved just behind the speed of the stator flux. The rotor will only ever achieve a percentage of the synchronous speed, and the difference is called slip speed. Cool. So now we look at slip speed and percentage slip. So whenever we talk about slip or percentage slip, we're talking about the difference between the synchronous speed and the actual speed. So as mentioned before, slip speed is the difference between synchronous speed and rotor speed. Although tough to visualize as something that is speed, it can be calculated with a simple formula. N slip is equal to the N synchronous speed minus the rotor speed. So slip speed can be represented with a value measured in RPM, but it's more often represented as a percentage difference between the two speeds. The formula to calculate the percentage slip is, so the percentage of the slip is equal to the N synchronous speed minus the N rotor speed divided by the synchronous speed, multiplied by 100 because we're trying to get a percentage. So often motors will have the rotor speed scribbled on its gear plate. However, some motors will give the synchronous speed and percentage slip. This slip is given at no load and is typically no greater than about 6%. When a motor becomes loaded, slip speed and percentage slip increases. So when a load is applied, slip is increased as there is resistance on the rotor. Even when there is no practical load applied, there's always a small degree of resistance through the bearings and air resistance. So a motor can only operate up to a certain value of slip speed before torque production becomes lower than the torque value required to shift the load. At this point, the motor will stall. Stalling is not good for any motor as current flow increases in the windings to a point where the motor could burn out or become irreparably damaged. Cool. So let's look at some percentage slip calculations. So first things first, we have a motor. Don't need to know the rating of the motor. We just need to know that it's spinning. Cool. So our synchronous speed. So N sync is 300 RPM. And so our synchronous, our rotor speed in rotor is 280 RPM. To calculate the percentage slip, so a motor has synchronous, for the next one, synchronous speed of 800 RPM and a slip of 8%. So the next one is an N rotor speed of 580 RPM and has a slip of at loaded 10%. Also just remember the formula. Percentage slip is N sync minus N rotor divided by N sync. So percentage slip equals N sync minus N rotor over N sync times 100. So you guys will be able to do the first one, and then the second one we'll walk through because it involves a bit of rearranging. Yep, so for that first one, we can go N sync minus N rotor. So 300 minus 280 over 300. Then multiply that by 100. Yeah, gives us 6.67% slip. So 6.67% slip. Cool. So the next one's a bit different. So we've got our slip percentage. So we can use our slip percentage to figure out our slip. So we already know this percentage has already been multiplied by 100. So to figure out this formula, what we do is we take our percentage slip and we divide it by 100. And then we can take our N sync. So that's equal to N sync minus N rotor divided by N sync. Cool. So now what we can do is multiply both sides by the percentage slip. Our N sync. So we multiply both sides by our synchronous speed. What we do is so we take our N sync, we multiply that, which means we can take our N sync from this side and we no longer have to divide that by that. So we have this formula. N sync times percentage slip divided by 100 is the same as N sync minus N rotor. So we figure that out. So we take our 800 RPM for our sync speed. And the first thing we do, take our slip of 8%, divide that by 100, and that gives us 0.08. So we multiply our synchronous speed by that of 800, and that gives us 64. Okay, so that 64 is the difference between our synchronous speed and our rotor speed. Cool, so what we can do is we can take our N sync and move it to the other side. So we erase this N sync here. We can move that to the other side. So it is a N sync minus, cool. So the formula ends up being our synchronous speed minus our synchronous speed multiplied by percentage slip divided by 100, which is the same as our slip difference. So N sync times 0.08 is our difference, so our slip, so our N slip. So instead of looking at the percentage slip, we're looking at the actual slip, and that will give us our N rotor. So it's basically 800 minus our answer of 64. So our rotor speed, or N on rotor speed, is 736 RPM. All right, does that make sense to everyone? The way I've yeah, I'll leave it up there for a bit. Oh no, my computer is trying to restart on me. Go away. Cool. Cool. So I'll work through the next one because that's also a bit complicated. So it's all about the rearranging of the formula. Do some revision later on. We'll come back to all that because we need to keep moving. So talk about rotor frequency. So because the current causing the mutual induction between the stator and the rotor is AC, current flow within the rotor is also AC. This AC must have a frequency, and the frequency is proportional to the difference between the synchronous speed and rotor speed and equal to the percentage slip in relative terms of frequency. So at startup, there's maximum difference between the stator and rotor. As in, the speed of the magnetic flux around the stator matches the supply frequency, and the rotor flux is 0. You could say that at the moment the percentage slip is 100%. This means that the rotor frequency being induced at the time of startup will be that of the supply frequency. So for example, motor connected to a 50 hertz supply at startup, the rotor frequency is 100% of the supply frequency, so therefore is also 50 hertz. This only occurs for a fraction of a second though. Once the motor is running, motor frequency will reduce to that of the percentage slip. This means that if the percentage slip is 5%, then the rotor frequency will be 5% of the stator frequency. So Example, this same motor is connected to a 50 hertz supply as a percentage slip of 5%, then the rotor frequency will be 5% of 50 hertz, 2.5 hertz. If a percentage slip were to reduce to 0% and frequency were to theoretically drop to 0 hertz, that means there would be no relative motion between the stator flux and rotor flux, and so no torque would be produced. All right, watch a motor explanation. Cool. So we've looked at how the basic operating principles. So now we'll have a quick look through the components. I know it's getting late, but we only have 3 or 4 weeks to get through all the material. Just going to try and get through as much as we can tonight. Cool. So we have what's called the yoke. They were talking about it in the video. So it's basically the part where the coils or the windings are wrapped around. It's made of silicon steel. It sits inside the motor housing around the outside. The coils are wound down the inside of those laminations of steel, and the paper you see there is the insulating paper that separates the actual coils or the windings from the yoke. Yeah, it allows for the electromagnetic induction because of the steel laminations. It allows that magnetic field to be induced around the yoke. And then you have the windings. They're coil copper wiring, usually laminated or resin, basically coated copper wiring to reduce the risk of shorting out the windings. Coils of copper wire formed into loops on the yoke, and they carry current drawn from the supply. Coils are one single conductor coated in varnish or lacquer to insulate each turn of the coil from the other. This leads to a high degree of inductance. Magnetic flux is produced by the windings and concentrated onto the yoke, and induces an EMF into the rotor in the best way possible. The configurations vary from motor to motor depending on the design and application of each motor, but they'll always be 120 degrees separate. So physically, they'll be 120 degrees from each other. They may have different poles, but they'll always be at 120 degrees from the other phases. Cool. So the rotor is the moving part in the middle that spins. So an induction motor, it's specially designed to have an EMF induced into it, so current can flow and produce its own flux. Introducing EMF into the rotor and produces torque to make the motor go round. All induction motor rotors are electrically isolated from the stator circuit, so they're separate, they don't touch, they spin inside of it. There's usually an air gap of at least 5 mil or more. Air gap between the rotor and the yoke of the stator, albeit very small. So the stator is the total outside the yoke and windings together. So that's what we call the stator. So there are different types. So 3 types of rotors in induction motors. So squirrel cage, double squirrel cage, and wound rotor. So the squirrel cage, so it's a cylinder made of laminated silicon steel with copper or aluminium bars feeding from one end to the other, joined together at each end with rings. So these bars are called rotor bars. The EMF is induced into the rotor and current flows along the bars, which in turn produce the magnetic flux. Rotor bars are typically skewed, meaning they do not run from one end of the ring to the other in a perpendicular fashion. They appear twisted when looking at them. This is to reduce the magnetic hum and give smoother rotation as is the consequent of each induction. So basically it looks like you took a cylinder and you kind of just twisted one end one way clockwise and the other end counterclockwise, and it just kind of twisted. If the bars were to run straight, the rotor would vibrate and the other bars would individually cut in the magnetic flux one at a time. You think of a steamroller rolling over a judder bar on the ground. If we were to take them on at 90 degrees, then the rollers would bounce up and down as they cross each judder. The steamroller crosses them at an angle, then there's at least 2 bars in contact with each roller at a time, reducing the juddering effect. A lot of earlier motors were designed like this, and so you can imagine it was didn't sound very good. So a double cage rotor. So a double cage is similar to a single cage, only a double cage has two sets of rotor bars. So if you look there at the cross section, it's got an inner and an outer cage, not just one. So higher resistance set closer to the surface, giving better torque at lower starting current. Inner bars have a lower resistance, so when the motor is running, most of the current then flows in those bars. Double cage has greater starting torque characteristics than single cage without the need for complex starting methods, but they have a lower value of pull-out torque. So they've got a greater starting torque, but a lower pull-out torque. So, which means it can be hard for the low torque to overcome the driving torque as the motor is accelerating. This is good for the likes of conveyors that stop and start when fully loaded. The downside to the double cage rotors are the driving torque falls away at lower speed than a single cage, so they can't be loaded as greatly for ordinary operation. The heat capacity of the outer cage is much lower than that of a single cage due to the high resistance, means they should not be used for constant acceleration of machinery. It can lead to the rotor bars overheating and burning out. The torque speed graph there shows the two styles of rotors. So you can see a single cage has a lower starting torque but a greater pull-out torque, so it can maintain higher torques at higher speeds. And the dotted line shows the acceleration of a fan as a load, which indicates that a single cage will be better suited as it can handle the low torque greater speed than a double cage. And here we have wound rotor. So wound rotor is a rotor that has a connection from the rotor itself to an external circuit. These rotors have windings within them that are connected to slip rings on the rotor shaft. A set of brushes are connected to the shaft and connected to the rotor circuit to external components. Circuit doesn't supply current through, though, however, it is a circuit that is connected to external control equipment that affects the performance of the motor. This control equipment includes resistors that adjust current flow in the circuit and therefore change the magnetic flux in the rotor. So it offers extremely high torque characteristics at low speed. It's used for applications like rock crushers and cranes. So since the inception of electronic motor control equipment, though, wound rotors are slowly becoming a thing of the past. They're usually large, cumbersome pieces of machinery that require constant maintenance and work. An electronic controller is able to reduce the size and costs associated with operating previously requiring wound rotor motors. Really annoying to say that over and over again. Cool. So here's a breakdown of the motor. You can see it's been exploded on the bench there. So you got your cowl at the back, which covers the cooling fan, stops people being able to put their fingers into it and pieces of large debris from getting in. You've got the rear end plate of the motor. You've got a hoist hook, and that's attached to the frame, which is the metal body of the motor. You've got a rear bearing. So that's actually at the back of the rotor. It's out the front of the motor, but it's at the rear of the rotor. You got the rotor itself there. You got the rotor shaft, the front end plate. It's the terminal box or your winding connections. That's where you hook the motor up to the electrical connections. The motor foot. So they normally you will either have a foot-mounted motor or a machine-mounted motor. So it'll either be mounted on the ground with feet, or to a piece of unistrut or a mounting frame, or it'll be mounted directly to the front. So the front end plate can also sometimes be where the motor is mounted if it's supposed to be mounted vertically or horizontally on a piece of machinery. You've got the stator, so that's the outside, the part where the magnetic flux is created via the input EMF. And you've got your front bearing there, which the rotor rotates inside to reduce friction. Cool. So there are standard components of an electric motor, whether it's single. So those are the components of an electric motor, whether it's single phase or three phase. Other components specialized to particular type of motors can include a centrifugal switch. So a centrifugal switch, just in case you guys haven't heard of it before, it's basically a switch that as the motor speeds up, clicks in and out. So it uses the rotational force. So centrifugal is what we talk about when we talk about rotational force. As it rotates, it's the force that pushes outwards. So if you've ever tried to go around a corner really fast, or someone's gone around a corner really fast with you in the car, you kind of get thrown towards the outside of the car. That's what we call the centrifugal force. You got your start and run capacitors. These are generally only on single phase. So single phase motors use capacitors to basically push, like when we talked about with AC theory, it pushes one of the phases. It causes one of the windings to be leading. So it causes a change in the phase relationship between the start and run windings, thus creating what appears to be a different magnetic field. So therefore changes the rotation characteristics of the motor. And then your power factor correction capacitor, this is normally for your three-phase motors, for your power factor because of the induction inside the windings of the motor. Your speed controllers, whether that be a variable frequency drive, a resistor drive, or just a potentiometer. Overcurrent, over temperature protection, so your thermal overloads. These are very important in high current motors. Once you start getting over, I think it's 375 watts, you need to start doing thermal motor protection. But generally, it's more for your three-phase than your single-phase. Because if you need a really grunty motor, you're normally looking at a three-phase machine. Cool. So motor cases. So screen protected. So a screen protected motor will have a solid metal casing around the length of the motor with a metallic screen or grill at each end. These often come with an integrated fan and force air over the internal parts of the motor for cooling. So they're used in dry, dust-free environments as their internal parts are fully exposed. Debris such as sawdust can collect around the internal parts and cause the motor to overheat. If metal swarf is drawn into the motor, conductive parts can short out, cause damage. Some of these motors come drip-proof, which means that the openings for ventilation are covered to prevent water from falling into the openings of the above, up to an angle of 15 degrees. These motors do give slightly greater protection from water ingress, however, are still not suitable for dusty areas or areas where water is splashed around at angles. These motors are often defined as ODP, or a open drip-proof motor. Cool. Just checking, who here has worked a lot with motors? So, or do you guys mostly do residential, commercial? Who's played around with motors out in the day? Okay, so Hayden and Liam, you guys play with motors a bit? Yeah, that's cool. Oh, I've got a few. Sweet. All right, well, I expect the guys who are saying yes, you guys will ace all the motor stuff at year 2 block course. Yeah, unfortunately, guys, I will see you guys at block course, but I will not be taking you because I am currently teaching pre-trade for this semester. I'll be taking block courses in the second half of the year. It's just the way it's worked out, but I will be there. Cool, so totally enclosed. So these motors have no external ingress into the internal parts of the motor and rely on other cooling methods. So there are 3 main varieties. TENV, totally enclosed, non-ventilated. These motors rely on natural convection to cool them. TEFC, totally enclosed, fan-cooled. So these are common motor that have a fan mounted to the rotor shaft at the rear of the motor. When the motor is running, the fan also spins, moving the air around. The fan is covered by a cowl that not only protects the fan, but forces the air to move away from the fan outwards and over the frame of the motor. And then you've got TEFV, totally enclosed, force ventilated. So they're designed to work in conjunction with variable speed drives. They utilize a fan that moves at a constant speed, despite what speed the rotor is moving. Thus, if the motor is not moving very fast, for some reason the fan still spins at speed and supplies plenty of cooling to the motor. Not listed here are the TEWC, totally enclosed, water cooled. And again, not very common, very specialized. Probably not going to see it. Again, I've never seen one in person at all. I think I've only heard of a couple and they've been overseas. Cool. Totally enclosed motors run hotter than open motors, and due to this, they rely on the frame of the motor to dissipate the heat. They are designed especially to try and counteract the effect of heating using following techniques. So the rotor and stator are longer than their axial length, meaning the flux density does not have to be as high, lowering magnetic and load losses. High quality silicon steel is used to reduce hysteresis losses. Large rotor bars are used as they are of a lower resistance, which lowers copper losses, and more copper wire with a larger cross-sectional area is used in the stator, offering less resistance and overall less copper losses. Cool, and then you have your flame proof and your explosion proof. So explosion proof motors are very similar to totally enclosed motors, only they're a lot more robust in terms of material thickness and strength. So they're used in places where flame or spark could potentially have catastrophic consequences, such as fire explosions. So places like this could include gasoline, petroleum plants, chemical factories, flour mills, and underground mines, or anywhere where there may be a risk of aerosolized particles becoming explosive or explosive atmospheres. So anywhere where there's gas or particles in the air that could ignite. Flour mills are a really good example because you wouldn't think normally, most people wouldn't think flour is explosive or combustible, but when you throw it up into the air and you spark or light a match, fairly decent flashover when it happens. Best video example, if you guys should know Mythbusters, there's an episode where they take an air, basically a pressurized compressed air, fire it through some coffee creamer. It's not flour, but coffee creamer with a road flare in it. And as the coffee creamer shoots up in the air and it mixes with the air, it catches fire and makes a really nice big fireball. Very much a don't try this at home, kids moment, but very good to watch to illustrate the point. So as well as the main frame, any joins and fastenings must also be explosion proof, along with the terminal box. All of these joins are designed to contain the explosion by means of lengthening the passage the energy must take. By spigoting any parts joining together, such as the terminal box lid, the energy is used up before it connects at the enclosure. Explosion-proof motors are often labeled EX on their nameplates. There are a number of subcategories and group of explosion and hazardous area ratings, which are dependent on the environment in which the motor will operate. So we'll look at those in a future topic later on. But yeah, if you're working in those kind of environments, you would know where to shop for these specialized motors. I think we looked at getting one and it was ridiculously expensive just for a demonstration model. Cool. So you got two different types of mounting methods. You got your foot mounted, like we saw in the previous photo. So foot mounting, so it has a base and you mount it to the ground or to a pedestal, and that's how you normally do it. So it's normally connected to pulleys or belt systems to the shaft. So a belt-driven system can allow for the motor to sit alongside the load, whereas a coupling system allows for the motor to be faced onto the load. This usually calls for very precise alignment of the motor to the load being driven, but flexible couplings can also be used in certain situations. So much less accuracy is needed if you're using a belt and pulley system, but if you're using a directly mounted shaft coupling, you need to be very precise about where your motor is mounted. The disadvantage of the foot-mounted motor is that if it is not mounted accurately, drive system can be misaligned for undue stress on the motor and the load. You got your flange mounted. So this is when the motor has a collar and a set of mounting holes around the front face to the motor so the shaft can be directly connected with the load it is to drive. This is often done on pumps and gearboxes. This method of mounting can really only be done with smaller, lighter motors, as it becomes uneconomical to suspend large, heavy machinery off of a flange. The advantage to a flange-mounted motor, though, is that the shaft can be directly coupled to the load with no risk of misalignment. You can flange mount bigger motors, but they require extra support on it to protect it from undue stress from vibration. All right.